Thank you. I'm going to talk today about the work I did in AT&T during this summer with Aman, Shaikh, Tim Griffin, and Jennifer Rexford on the interaction of OSPF and BGP. And you're going to see how hot potatoes are hitting up our BGP routing. So first of all, most people, when they think about BGP, they think about intradomain routing mainly. And then talk about, okay, routing inside an AS, they think of OSPF, ISIS. But in large transit ASs, most of the traffic is actually routed using BGP. And IGP changes, so things that happen inside the network can and do have impact in the BGP decisions. So in this work, you're trying to understand how these interactions happen, and mainly it happens because of hot potato routing. So let's look at this simple example of an ISP network where we have routers in San Francisco, New York, and Dallas. Imagine now we have a destination outside, so external destination to this AS with two equally good routes that are learned in San Francisco and New York. And Dallas has these two options of routes, one with cost 9, IGP cost 9 to reach the destination, and the other one with cost 10. So in this case, hot potato routing tells us that Dallas would choose the exit point with closest IGP distance to forward traffic to this destination. So imagine now that something internal happened, a failure or some plant maintenance or even traffic engineering that made the cost from the path to Dallas to San Francisco to change from 9 to 11. So now in this example, all the routes that are being forwarded through San Francisco are going to start using the exit point in New York, and that's what we are calling here a hot potato change. So the BGP routes look the same, it just changed because of the IGP cost. In this example, I'm just showing it for one destination prefix, but in a big transit network, you may have thousands of destinations shifting from one egress point to the other just because of a small cost change inside the network. And this has consequences so during the time that the traffic is shifting, you may have transit routing instability, and the traffic shift may cause congestion in these paths, which will cause delays and losses. And some of these may be exported to external BGP to your neighbors. And the reason that there is this interaction between these two is that BGP uses IGP information in its decision process. First of all, of course, it has to check if the next hop is reachable, and it uses IGP. And then if all the other attributes look the same, so if the routes are equally good from BGP standpoint, then it's to do the hot potato check, so to check which one has lowest IGP costs. And in this work, what we want to understand is, so what's the impact of hot potato routing in a real network? So why do we care about hot potatoes? So first of all, there is a large number of prefixes that can be potentially affected. So all prefixes that we learn from peers are learned in lots of different POPs and may be affected by hot potato. And all multi-home customers, so the customers that pay more, also may be affected by hot potato routing. So we want to understand the impact in a real network. So how often does hot potato routing causes BGP routes to shift? And when these changes happen, how many prefixes are impacted? What's the fraction of our BGP table that's changing because of this shift? And also, what's the delay from an IGP change to the time that the BGP routes are converge? So, and ultimately what we want to do is to try to avoid routing instability caused by hot potato. So operators should try to minimize the number of times that the hot potato changes happen. And for the vendors, the message is, so how, if the hot potato has to happen, so if you have to change your BGP routes because something happened inside a network, how can you minimize the impact of that by making this interaction as smooth as possible? Our approach to do that is we measured hot potato changes in AT&T's network. So we collected measurement of both OSPF and BGP messages in the common backbone for AT&T. And we have one OSPF monitor that collects all the link state advertisements, and a BGP monitor that has feeds of tables and updates from at least one router per POP in the common backbone. We pre-process these messages to cluster them in time so that we can get clear events for both the OSPF and BGP. And then we correlate these two streams of data. So the idea here is to emulate one operational router, and we can see all the changes, the OSPF changes from that router point of view, and also the BGP updates that it sends. Here's just an example of how we do this matching. So first we have to transform the stream of OSPF messages, the LSAs, into changes with the router that we are trying to emulate, the point of view of that router. So imagine that we have this series of messages, refresh, link failures, weight change, things like that. And then we transform them to this router point of view. So refresh messages, we don't really care about them. So a link failure may cause the paths from our point of view to a lot of the egress points to change costs, may cause some of them to be deleted. And so we just classify that. We also look at the BGP side. We get a stream of BGP updates. I'm not going to explain exactly how I do this. If you are interested, then in my webpage you can find some more detail on that. But we classify all the BGP updates according to how, if they could be caused by an OSPF event or not, and which kind of OSPF event could cause that update. And then we match them in time. So in this case, I put an example of this path cost change that caused a couple of BGP updates to happen. So how much, now I want to try to answer a question. So how much of this really happened in the AT&T network? So I'm presenting here some results that I found for June last year, and I'm presenting the results for two routers. I chose one router in a POP with rich peering, so where AT&T peers with all the big guys, all the tier ones. And another POP with no peering, so there is no peering in that POP. And we see the first table, it shows the percentage of updates in a day that was caused by OSPF. And you can see that in a POP with rich peering, it doesn't really have much OSPF hot potato related updates. But in a POP with no peering, it varies from, of course, there is some days that there's no updates that are caused by hot potato, but there are some days that go up to 46% of the updates in a day that were caused by hot potato. And you can see the last column of this table, it shows you for the month of June, the percentage of days, the number of days that had more than 10% of updates caused by hot potato. And in this, for the non-peering router, we see that there were 5 days. So now you answer the first question, hot potato does happen, and it can have some impact, but how much is this impact? So now we have the second table that shows for one LSA, one OSPF LSA, what was the impact that it caused. The good news is, so most of the LSAs, around 95% for both routers, doesn't cause any impact. So it doesn't impact, it doesn't generate any BGP update. But for a small percentage of the LSAs that do impact BGP, they can have a significant impact. For the router with no peering, we saw a day in which 59% of the BGP table changed because of one single event inside the network. So we understand now that this hot potato can have a significant impact, but how long does it take after the OSPF change happened for the BGP updates to come out? So we can divide this delay in three different parts. First, the router has to learn after the OSPF converges and the OSPF route is installed. You have to revisit your BGP decision and see how long does it take. So this depends a lot on the implementation in the router, and there are different ways of doing it. So you can do it a timer based. So every X seconds you run a process that will revisit your decision, and then you're going to update your BGP routes according to your OSPF information, or it can be event-driven. Whenever something happens in OSPF, that is going to be reflected into a BGP decision. After that, so in the case of AT&T and lots of big networks, there is an IBGP hierarchy, and you may also have to wait for your route reflector to tell you that you're of the new route. You may not know of the route that has the shortest path from you now. And so that's something that's another delay. And all these two first points takes the delay from once the OSPF change happened until BGP learns about the change. And then, of course, if you're changing 59% of your routing table, it may take a while to transfer all these updates until the last update's going to come out. So let's see now what first of all, so that's one thing that's very important. So these delays are very sensitive, both to the router implementations and the design of your network. And I'm going to show here one example that we saw in the AT&T network. First, this graph, it shows the time difference. So when I saw the LSA to the time that I saw the first update that came for that LSA. And in the y-axis, you see the fraction of hot potato changes, cumulative fraction. And first of all, let's look at the blue curve. We did some lab experiments with a router, and we can see that in this case, we have a uniform distribution in the range from 0 to around 60 seconds, which suggests that this router had a timer-based implementation for the OSPF BGP interaction. So in this straight line just means that the OSPF event can happen in any time in this range from 0 to 60, and depending on when it happens, then it's going to see a higher or lower delay up to 60 seconds. You can see that then the two other lines, it's for the operational routers that we are emulating using the data we collected. And one line is for the month of June and the other for the month of September. And you can see that it also has this 60-second timer. Of course, the line is not so straight because I just used, the events that happen in the network, and there are not as many samples as the blue line. But you can also see that there is this part of the curve there in the end that has a little bit longer delays, and we conjecture now that that's because of the IBGP hierarchy, that we may have to wait for 2 runs of the timer for some of these routes. Now let's look at how long does it take for transferring all the multiple prefixes. Again, I'm showing the time between the LSA and the BGP update. And here I just chose 3 sample events that caused lots of updates, and I'm showing on the y-axis the cumulative number of hot potato changes. And it's just the cumulative number of updates that particular OSPF event caused. Let's just look at the red curve, because all of them are similar, just different events. So we can see that it starts around 25 seconds, let's say, and so that means that the BGP process run at 25 seconds after the OSPF event happened. And then it can take it took 81 seconds to transfer all this, because this event caused more than 80,000 prefixes to shift. And so the bottom line here is that in the worst case scenario, it can take around 100, 120 seconds to revisit your decision, and then you may take 80 seconds more to transfer all the routes. So the last prefix may take up to 3 minutes to get updated, to get installed in the FIB. And we didn't even count the time actually to install the prefix in the FIB. So what the implications that this have for forwarding packets? So first, the FIB is only going to be updated when both your IGP and your BGP converge. So people talk a lot about the IGP converge. That's important because, of course, that has to happen first. But if your BGP didn't converge, all your external routes didn't converge yet. And the second question we had is, do the measurements we have today to measure the customer experience and of the network, do they catch these kinds of performance degradations? So first, let's look at how this can impact the forwarding conversions. So imagine now this example in the top, where we had routers R1 and R2 both using the egress points to your right there. And imagine that the cost to that link changed from 10 to 111. So what's going to happen is that in the end, both R1 and R2 are going to shift to the egress point in the left. But depending on the order that the timer runs, the BGP decision is revisiting each of these routers, what can happen? Imagine this following scenario, that the R2 revisits its decision first, then it starts using R1 to forward packets to this particular destination. Then R1 runs, but you don't know how long it's going to take. It may take up to 60 seconds for R1 to revisit its decision. And all this time, the packets to the destination are going to be caught in a loop between R1 and R2. And now let's see how can we detect these loops? Can you measure this? Can we see if these are actually happening in the network? So today, the way that the measuring of the customer experience work, we put two machines, W1 and W2, that will try to measure this. But this loop is only happening for this particular destination. So if you probe from W1 to W2, even though you're probing the same path, you're not going to catch, your traffic is not going to be caught in this loop. So now how can you avoid unnecessary changes? Of course, sometimes you just have to change, but can we do something? Can we try to avoid it? So we see that with the router in a POP with no peer, see many more of these changes than a router in a POP with rich peering. So how can we play with the topology to avoid these changes? And also, can we do planned maintenance in a better way that will not cause these hot potato changes? So first, look at these three toy topologies here. You can see that the topology, so if from Dallas to San Francisco you have just cost 10, and from Dallas to New York have cost 10, any little change in your network is likely to make the shortest path shift. And so this is much more prone to have hot potato changes. Whereas the other two, so if Dallas is really close to San Francisco and really far away from New York, there has to be a big change in the network to Dallas to shift from one to the other. And the same thing in the bottom one, if you have multiple paths that are equally good in terms of IGP distance, then it's also harder for it to change. You may be thinking, oh, of course, it's very easy to do that in the toy examples, but how can I do that in my network? So, yeah, I don't have the answer for that yet, but it's just to give you some food for thought. You know your network, and you may be able to. So it's just something else that you should think of when you do your traffic engineering, when you're doing your planning, and tools for doing that. Yeah, of course, we have to work on that. And something else that you can do is, if you look at, so how can we, if you're doing maintenance, so imagine you have to do maintenance in the path from New York to San Francisco, and that's just, again, a tight topology. And now all your traffic is going through San Francisco, and you want to take out this link, you want to do maintenance there. So what can you do? So if you just put it to a very high cost, all your traffic is going to start using the exit point to Dallas, and you're going to have all the penalty of doing the hot potato changes. But if you think of it ahead of time, you can change the cost of that middle link from 10 to 4, and then you can cost out your link, and all your traffic going to still be using the San Francisco egress point. Of course, you have to wait for OSPF to converge in that example, but all your BGP routes won't change. So the convergence is OSPF time is seconds instead of minutes. The traffic is much more predictable, faster, and again, as I said before, you have to judge how much of you can do in a real network like that. But it's important to have tools that will predict these kinds of changes and will give you answers for that. So in conclusion, we showed that hot potato can have an effect in a large number of prefixes, and it does have higher convergence delays. So for the vendors, the message here is event-driven implementations of the IGP, BGP interaction will help to minimize some of the effects. Of course, you still have to wait for the path vector protocol to converge on top of the link state, but at least the timer effect is it's something that amplifies the convergence delay. And also, once you do your studies, you have to look at in a more like network-wide effect, not only in the box level, because these events, they are very hard to see how they happen in the box level. And for the operators, of course, you can tune your timer. You know how your network is. You know how low you can put the timers down. I can tell you what the right values are. And you can try to play with some of the examples we showed here in how to set up your weights and to do maintenance in a way that will avoid hot potato changes. In our side, we are trying to do some work into quantifying the impact of hot potato changes in shift of traffic, also trying to see if you can catch these loops in the commercial network to see if it's really happening, and also quantify how much of it is exported to our neighbors, because most of these updates probably just IBGP updates and don't go to the neighbors, but we want to quantify how much of it is happening. So anyone has any questions? No?
Hi, Rob Renison, Laurel Networks. These are probably simple and first of all, regarding the how we would react, yeah, we would listen to RIB changes, and obviously there'd be event-driven then. So if BGP was trying to resolve its next hop, it listens to the IGP change and would fail over in milliseconds. And then an observation, which is the fact that for some failures, even in like your first slide, the simplest of case, the only real way to measure, there would be no routing change because BGP would just resolve its own next hop, fail over to another link, and the only way you could see any problem there would be by traffic analysis and seeing some traffic loss.
So I didn't understand, but we did measure this in the network. So BGP, there are BGP changes.
No, yeah, what I'm saying is for the simplest of topology with one router, one speaker advertising next hop self, and he's got two links to go to, and one of them fails. He changes his own view of what the next hop is, and there's no impact. He doesn't withdraw the routes. He just fixes 100,000 prefixes go to a next hop. So in the simple case, you're not going to see problems. Now, obviously, in a real network with a more richly connected topology, you may see changes.
I'm sorry, I think so my example, it was not a link, it was a path. So yeah, that's why I didn't cut this squiggly line, because...
Okay.
Yeah, but...
And another question was, that's probably because I'm not getting your simple example, but in terms of correlation, so an LSA is withdrawn, once again, that's withdrawn for finding the next hop. I'm a speaker and I'm advertising next hop self, and I see an LSA withdrawn for how I get to my next hop, what I've learned via IBGP. How do you correlate the LSA for the prefix that I'm using to forward the routes with, you know, the fact that I've suddenly started withdrawing all these prefixes? You know, there's a time thing about, oh yeah, 100 prefixes were withdrawn, but there's no, I don't announce what was in that LSA.
So, yeah, we look at the LSAs, and we look at how the LSAs affect the table for that particular router, and we look at the BGP update, and we see what kind of update it is for which next hop, and then we match them in time.
But if I'm announcing next hop self, then, or I'm withdrawing routes, it's still difficult to correlate because myself hasn't changed. The LSA was one that I was using because that was announced by my IBGP peers.
No, but we get, so the data we have is all IBGP data, and so we get all this information. It's, yeah, for these routers.
Okay, well, we can draw a picture offline or something. Okay.
Yeah.
Thank you.
Okay. Thank you.